All right, so we're in this chapter in thermodynamics about applying the conservation of energy to open systems to control volumes. And so we'll have a system, you'll have some heat transfer in, you have some possible work transfer out or power out. This is a rate and a rate. And then you could have some mass transfer as well as mass transfer in and out. We apply it, the general equation for conservation of mass and conservation of energy, to nozzles, diffusers, pumps, turbines, compressors, heat exchangers, throttling devices. So let's just keep working through. Here's a problem. Air enters a well-insulated diffuser at 95 kilopascal, 270 Kelvin, and 150 meters per second through an area of 0.2 meters squared. It exits with the given velocity through an area of 0.55. What happened to the area? It went up. The exit area is greater. That's a diffuser, classic example of a diffuser. Air behaves as an ideal gas. Assuming steady state operation, determine the mass flow rate, something like m dot. The exit temperature, probably T2, and the exit pressure, P2. So we make a sketch of our device. Typically a diffuser shown like this, and we have inlet state 1 and exit state 2, and we just start listing. Okay, it's coming in at P1 of 95 kilopascal. P2, well, we don't know that. We're asked to solve that for part C. What about T1? Well, it comes in at 270 Kelvin. And I could put V1 is 150 meters per second through an area A1 of 0.2 meters squared. Now, I'm going to try to list the same properties like T2 and V2 and A2. The order really doesn't matter, but whatever system you have to organize the information. And so we see that A2 is given in the problem statement as well as V2, isn't it? 49.6 meters per second and 0.5524 meters squared. Now, this is a made-up problem. And when you see a number like the area 2 to 4 significant digits, something's going on. Let me just tell you what something's going on in the background. I made this problem up and made sure it was physically possible so it didn't violate the second law of thermodynamics. And so this is frictionless flow. This is inviscid flow through this diffuser. It's isentropic flow. You may not understand all those terms, but by the end of the semester we will. It's reversible flow through that diffuser. So there are limitations comes by the second law, and this one is a great diffuser. But to make things work, I basically had to go in and pick the 4 significant digits, that area and that velocity is 3 significant digits. So that's something, you know, it's like I didn't want to make a problem that violated the second law of thermodynamics. That would be bad. All right, so let's continue on. Air behaves as an ideal gas, assuming steady state operation, determine the mass flow rate. Well, the mass flow rate, you introduce a control volume. Sometimes I forget to do that. There's our control volume. And for this diffuser, you say, what is the rate of heat transfer into or the shaft work out of that control volume? It's 0. What about the changes in the elevation across, the change in potential energy for flow going in and out? That's 0. And it's running at steady state. All right, so our energy balance equation, should I write down the whole equation? You got it? So it would be that the 0 is equal to m dot h in minus h exit plus specific kinetic energy in minus specific kinetic energy exit. Just one mass flow rate. What's in is out, and then the energy balance gives us the relationship. Why didn't I cancel and say the change in kinetic energy is 0? Well, it wouldn't be much of a diffuser then. The purpose of the diffuser is going to slow it down. When it slows down, the kinetic energy drops a little bit. Okay? All right. So how do I calculate that mass flow rate, m dot, this mass flow rate right here going through the system? Well, it looks like I'm given the area 1, the velocity 1. If I could get the specific volume at state 1, would that allow me to calculate the mass flow rate? Sure. And I recall that PV is equal to RT. So P at 1, V at 1, T at 1. So let's go ahead and calculate V at 1, which is, I'm going to put R bar T1 divided by the molar mass of air, P1. I think all of those are doable. You've done that before. So let me just give you that the specific volume at 1 is 0.81565 meters cubed per kilogram. Once I know that, I stick it in here. I know the A1 and the V1, and I get that the mass flow rate through the system comes in at 36.78 kilograms per second. In my calculator, I'll store 5 digits on that, or 6 digits. I keep all those digits in my calculator because I may need it for the next step. Right? But for the answer, I'll round off to 4. All right, 36.78 kilograms per second. What's the exit temperature? Well, when you see temperature, you think energy. So let's take a look at when we say it's ideal gas behavior, there's 3 things that come out. 1 is PV is equal to RT. 2 is internal energy is a function of temperature only. Is a function of temperature only, and enthalpy is a function of temperature only. True? So this enthalpy right here is a function of temperature only. So what we do is we'll say, we'll solve for H2. And it's a function of temperature only, and then I'll solve for T2 using the table A22, the air tables. All right, so from the energy balance, H2 is H1 plus kinetic energy 1 minus kinetic energy 2. So it's equal to H1 is evaluated. Maybe I come down here and I say, well, H1. Well, H1 is a function at 270 Kelvin. And I go to the air table and I find H1 is 270.11 kilojoules per kilogram. Again, that's out of table A22. All right, so this comes in at 270.11 kilojoules per kilogram plus 1/2, and then the kinetic energy, V squared 1, that's 150 squared, minus V squared 2, 49.6 squared. That's meters squared per second squared. And then we use that conversion factor. That 1,000 meters squared per second squared is precisely a kilojoule per kilogram. Don't forget the 1,000. A lot of people will forget it. I mentioned it already. So we calculate that H2, the exit enthalpy, from an energy balance statement gives us that it's 280.13 kilojoules per kilogram. I now know what H2 is, 280.13. Just like before we used T1 to get H1, I'm going to use H2 to get T2 in table A22. So we flip through the table A22 and we say, somebody made up this problem. Because to 5 significant digits, that number is perfect in the table. And it turns out that this T2 then is 280 Kelvin to 5 significant digits. So it's a made-up problem. You know, that's nice. So we don't have to interpolate. But if it fell in between, we just have to do a little interpolation. True? Okay. So what did the temperature do when it went through that diffuser? The temperature went up. The temperature went up. All right. This is isentropic flow through the diffuser. It's perfect flow through it's like a frictionless pulley in statics. All right. So let's go ahead now and solve for the exit pressure. How do I find the exit pressure? Well, I've used the energy equation. I've used the mass balance equation, but we still have an ideal gas behavior. And so can I calculate from the mass balance equation that, here, let me try this. Try and squeeze it in down here. The mass flow rate at 2 is the mass flow rate. We know that, true. It's 36.71 kilograms per second. And that's equal to the area at 2, the speed at 2, divided by the specific volume at 2. I look at this equation. I know the m dot. I know the area. I know the speed. I can get the specific volume. So we calculate the specific volume at state 2, and we find that it's 0.74493 meters cubed per kilogram. Now that I know the specific volume, you use the same equation, PV is equal to RT. So we have that P2, V2 is equal to, I'll put RT2, and we say, I know T2, I know V2. The only thing I need to solve for is P2, because it behaves as an ideal gas. And we find that the final pressure from this equation is 107.9 kilopascal. So what happened to the pressure? It came in at 95. It went out at 107.9. There's a pressure recovery. Pressure recovery. When I teach fluids, I emphasize 3 forms of Bernoulli's equation, and one form is the pressure form. The other is energy per unit mass, and then the energy per unit weight. All right. In the Bernoulli's equation, it's really a conservation of mechanical energy statement. And in the pressure form, energy per unit volume, guess what the units on P are? P is force per unit area. If I multiply by M and M, I didn't change anything, meter over meter. What is a Newton times a meter? Joule. What is meter squared times meter? Meter cubed. You can interpret pressure. I know we don't like to do that too much, but you can interpret pressure, and it's often very useful to interpret pressure as energy per unit volume. So what happened is that some of that kinetic energy was converted back into energy per unit volume realized by increase in pressure. Just opposite of the nozzle. There's a pressure decrease in the nozzle to make it go out fast. In the diffuser, there's a pressure increase because it's slowing down. Got it? All right, let's move on. Heat exchangers. Well, there's at least, whenever you see a heat exchanger problem, do this. Read slowly or carefully. Read slowly. Read the problem slowly. Read the problem carefully, because it could be a heat exchanger problem where I have a hot fluid stream, a hot fluid, or a hot side, and I have a cold fluid, and I have basically heat transfer between 2 fluids that don't mix. A heat transfer that goes from the hot to the cold. But it's well insulated on the outside such that Q dot to the surroundings is equal to 0. There's no heat transfer to the surroundings. A heat exchanger that has no heat transfer to the surroundings sometimes is worded like an adiabatic heat exchanger. Well, they use this word, adiabatic. Okay, well, adiabatic meaning no heat transfer. That sounds like a bad heat exchanger. No heat transfer in my heat exchanger? Well, it's no heat transfer to the surroundings, but there's a lot of heat transfer inside where you want it to occur. True? So what we do is we introduce states like 1 and 2 and 3 and 4. And we do an energy balance for the control volume. And for that control volume that encompasses the whole heat exchanger, Q dot's 0. That's why we'd say it's an adiabatic heat exchanger. There's no heat transfer with the surroundings. But inside, there definitely is. But Q dot, when we write the energy balance for this form, we would get the mass flow rate of the hot fluid times a change in the enthalpy. Think about this. Is H2 greater than H1, equal to H1, or less than H1? What happens to the enthalpy of the hot fluid as it's flowing through the heat exchanger? It goes down. And why does the enthalpy go down? Because there's heat transfer from the hot side to the cold side. Heat exchangers aren't magic. If I have a hot fluid in communication with a cold fluid, the hot fluid gives up some, it's transferred out, and the heat transfer out of the hot fluid and into the cold fluid. Kind of just keep reminding yourself of that basic fact. If it's going to be transferring energy out of the hot fluid, the enthalpy of the hot fluid is going down, just like the temperature of the hot fluid is going down typically. Okay, so it's H1 minus H, let me leave this in the same color, H2, and then that's mass flow rate of the cold fluid times the enthalpy 4 minus enthalpy 3. There's an enthalpy gain in the cold side. All right, but that's not the only type of heat exchanger. Sometimes they'll just say I have a fluid going into a heat exchanger and the fluid is hot. And it comes in at state 1 and it goes out at state 2, and there's a heat transfer out. I'm going to draw it like this. Q dot out of the heat exchanger. We do an energy balance for this heat exchanger. This heat exchanger is not adiabatic. There's a heat transfer across the boundary. And so then what we would have is we'd have the mass flow rate of the hot fluid times the enthalpy 1 minus enthalpy 2 is equal to what is coming out of that heat exchanger. Where's it going? Somewhere else. Okay. There's another heat exchanger. You might want to draw it like this. And we have a cold fluid, and we'll call it, I'm going to just use state 3 and state 4. And this is a cold fluid going through it. And we only have that as a description of the heat exchanger. And when we do a control volume analysis around it, CV, what do we say? Well, there's going to be a heat transfer into the cold fluid from the surroundings, Q dot into the cold fluid. And when I do an energy balance, we'll have that the mass flow rate times the cold fluid of the cold fluid times the enthalpy gain is equal to the rate of heat transfer into the cold fluid. True? And you could put both of these halves together and get back to the original. That's why I'm trying to draw it that way. But you have to read heat exchanger problems carefully because sometimes they're just given a heat transfer, or sometimes they're said, oh, it's an adiabatic heat exchanger with a hot side and a cold side. All right. Often I fail to mention this. Often the change in the kinetic and the change in potential energy are neglected for heat exchangers. That's a standard assumption. And for a heat exchanger, is there any shaft work cutting across the boundary? No. No. There's no shaft work cutting across the boundary. So I should have mentioned those earlier. All right. Ready to solve a problem? So we have a heat exchanger. It's used to condense steam. That's the purpose of this heat exchanger, to condense steam. The steam enters the shell side of the heat exchanger at 0.3 bar, 95% quality, and at a flow rate of 10,000 kilograms per hour, and leaves as saturated liquid. So try to be a little, what we'll do is we'll put a heat exchanger like this, and what we'll do is we'll have tubes running through the heat exchanger, and on the outside of the tubes, all the tubes are contained in a shell. And so on the shell side, maybe we're bringing in the top at state 1, some steam, and then we're going out at the bottom at state 2. So that's all on the shell side. Maybe we have end caps so that the fluid comes into the end caps and then spreads out and can go through the tubes, and then are collected on the other side, and then it goes out again. Okay? This will be a shell and tube heat exchanger. All right. The fluid can come in this way and go out that way for state 3, and this would be state 4. Go out that way, state 4. So 1 is this steam that's going to condense. They say it's going to condense. The steam leaves as saturated liquid. Okay? So maybe I start organizing. I'll say this is all state 2, it's saturated liquid. What about the description of state 1? How would you describe state 1? Well, it enters at a pressure of 0.3 bar and a quality of 0.95, 95%, 0.95 or 95%, and at a mass flow rate of 10,000 kilograms per hour. Using that information, how would you describe state 1? Is it saturated liquid? What is it, state 1 description? It's what? It's two-phase. Liquid vapor. Mixture. True? Isn't that what it is? Okay. What about the pressure at state 2, the quality at state 2, the mass flow rate at state 2? Can we deduce any of these? We can say the quality is 100%. Saturated liquid, 0%. Sorry, 0%. True? All right, what about the mass flow rate at state 2? Can I deduce that? It's the same as the mass flow rate at state 1. What's on the shell side stays on the shell side. There's no mixing. There's heat transfer through the metal walls of the tubes that separate the two fluid streams. All right. And what about the pressure at 2? Any information given about the pressure at 2? What would be a reasonable assumption about the pressure at 2? Same pressure. It's a heat exchanger. When you have flow through one side, you want to minimize the pressure drop. And as a good first approximation, you neglect the pressure drop. Pumps add pressure gain. Restrictions, valves, they have pressure losses. Nozzles change in pressure. Diffusers change in pressure. But heat exchangers, unless there's information given, it's negligible. So that's P1. So it's 0.3 bar. All right. Let's go now and talk about state 3 and state 4. Lake water flows through the tubes in the heat exchanger, entering at 21 degrees C. So we have 3 coming in, so I'm going to put T3 equal to 21 degrees C, and leaving at 29 degrees C. It's lake water. So lake water. What do you think about the state of the fluid? How would I describe it? Is it superheated vapor? What is it? Condensed liquid. It's liquid. It's liquid. It's definitely not even close to changing phase. Okay? If I had to guess the pressure, what pressure would it be? 1 bar. Yeah, lake pressure. Yeah.
So is the lake water is basically what's doing all the cooling?
Yep. So which fluid stream is my hot fluid stream, and which fluid stream is my cold fluid stream? The steam is hot. The steam is my hot side, And the lake water is my cool, I'm going to just say cool instead of cold, right? Cool side. And so inside the heat exchanger, which direction is the heat being transferred? From the steam side that's condensing to the lake water side, which is going to come out warmer and be heated up. All right. Now, what is the flow rate of the cooling water? What are they asking me? Are they asking me for the flow rate of the steam or the mass flow rate of the lake water? Which one? It's lake water. It's lake water. True. They gave us the mass flow rate of the steam, 10,000 kilograms per hour. So how do we solve for m dot of the lake water? Introduce a control volume. Apply conservation of mass, conservation of energy. The mass, two streams don't mix. We already talked about that, right? So that one's easy. Let's now move to conservation of energy. When you do conservation of energy, you'll have two inlet mass streams, two outlet mass streams. You combine the two inlet mass streams and the inlet and exit for the same. And what you get for the energy balance is that the mass flow rate of, I'm going to call it M.1, M.2, let's call this the mass flow rate of the steam. I know it's going out liquid, saturated liquid, but we'll just call it M.S. Okay? Times comes in high enthalpy, goes out low enthalpy, true? Equal to the mass flow rate of the cooling water or lake water, LW or CW, some subscript like that for cooling water or lake water, times the enthalpy. It goes out at 4 and comes in at 3. Is that a good energy balance? So if I wanted to solve for the mass flow rate of the lake water, it would be the mass flow rate of the steam, which is given, H1 minus H2 divided by H4 minus H3. I need those enthalpies. All right, H1. How do I get H1? Is it the H of F plus the quality 1 HFG at that 0.3 bar? Yeah. And so we calculate the enthalpy at state 1. It's 2508.5 kilojoules per kilogram. What about H2? Saturated liquid. So is it H of F at that pressure, which comes in at 289.23 kilojoules per kilogram. Okay. Now the enthalpy at state 3. Liquid water at 21 degrees C. H of F at 21 degrees C, which comes in at 88.14 kilojoule per kilogram. And H4, that's liquid water saturated, it's approximation, H of F at 29 degrees C, which goes at 121.61 kilojoules per kilogram. So when we calculate the mass flow rate of the lake water or cooling water, we find that it's 663,000 kilograms per hour. So 10,000 kilograms per hour went that way. 663,000 kilograms per hour went the other way. This is a big power plant. All right. How do we cool power plants in the state of Texas? We build a lake and we dump the heat to the lake. That's pretty common. If you have a river nearby, you can take some into the river and then dump it back into the river downstream if the river flow rate's constant, etc. Our river flow rates, probably not as well. We actually sometimes will pump it out of a river into a lake and then let the lake level be constant. Okay. Any questions on that problem? Let's continue on. Throttling device. Well, we're getting near the end. Sometimes you have fluid come in and you have to go into a device and all it does is throttle the fluid. It's like a partially closed valve. Okay? Sometimes they're controllable. And so inlet 1 going that way, exit 2. So, I would talk about the pressure 1 and the pressure 2. I have a partially closed valve. Can you tell me a little bit about what the pressure should be if the flow rate's flowing from 1 to 2? Do you think the pressure is going to be different across the partially closed valve? Yeah. Which one's this? So this pressure 2 is going to be less than the pressure 1. It's a pressure drop across the throttling device. All right. Now, what we do is we come in and we do an energy balance. And for this throttling device, do I have, what do you think about Q dot? Is it a heat exchanger device? No. It's approximately 0. How about any shaft work in or out? No. And we typically neglect changes in kinetic energy and changes in potential energy. So let's write down for this control volume the grand form of the conservation of energy equation. Rate of change of energy inside that control volume with respect to time is equal to rate at which energy is flowing in by heat minus rate it flows out across the control volume boundary, typically by shaft power. If you have electric power, you can group it in there too. Plus, it comes in at state 1 with enthalpy 1 and goes out at state 2. Enthalpy 2 comes in with the kinetic energy, goes out with the kinetic energy. Goes in with the potential energy, goes out with the potential energy. Can't do this. PE2. Did I write it? Okay. This is one inlet, one outlet, so I combine those M dots. And why is this steady state? 0. No heat transfer, no work. Negligible changes kinetic, negligible changes potential. So what do you deduce about the change in the enthalpy across a throttling device? There's no change. This is a big, like, what? So this no change in the enthalpy is called isenthalpic. It's isenthalpic. Constant enthalpy. Think of another word, isothermal. What was constant? Isothermal temperature. Isobaric. What's constant? Pressure. Isochoric, you don't know that one very well, but it's constant volume or specific volume, isochoric. And now we have isenthalpic. It's constant enthalpy. And when we get to entropy, we'll have isentropic. So try to learn a little vocabulary here. Okay. Now, if I put air through here, which is an ideal gas, and H is a function of T only, guess what? If it's air going through a throttling device and delta H is equal to 0, talk about delta T. What's the change in temperature? 0. But often we don't put air through a throttling device. That's not purposeful. We like to put refrigerants. What do you mean by refrigerants? Refrigerant 134A. We use it all the time, throttling devices. And what we bring in is we bring in something that is high pressure and in the liquid state, slightly subcooled liquid. You can sometimes just bring in saturated liquid. When we put that through, something surprising happens, which throws students completely through the loop because they say, hey, if it's no change in enthalpy, no change in temperature. True for air. You're absolutely correct for air. Put a refrigerant, a liquid refrigerant, high pressure in. What's going to happen across it? Guess what the temperature does? Goes down. That's impossible, Professor. How can you have a fluid going through this simple little device and it comes out cold? There has to be heat transfer to make things go cold. True or false? In your mind, that's what you're saying. Hey, I have to have a heat transfer to make it cold. Is there any heat transfer across the throttling device? None. It comes in sometimes hot. You can touch it and feel it. Ooh, this is warm. Right on the other side, frost on the line. You touch it, you could get ice. You could get cold. It's cold. It's not just a little cold. It's really cold. Impossible. Nope, it's not impossible, and that's the magic of refrigeration systems. We'll spend a little more time on it, but let's solve a problem. Ammonia is a good refrigerant. So ammonia at a flow rate of 0.2 kilograms per second at pressure 12 bar and 20 degrees C flowing into a throttling device and exits at a lower pressure of 1.5 bar. So let's go ahead and start organizing information. Inlet state 1, exit state 2, it's flowing that way. We'll talk about the mass flow rate at 1.2 kilograms per second. What's the mass flow rate at 2? 0.2 kilograms per second. It's the same mass flow rate. You just drop the subscripts. M dot is M dot because you do a control volume analysis and mass balance. What comes in goes out, steady state. Let's go ahead and continue to organize information. P1 is 12 bar. What's P2? 1.5 bar. What is T1? 20 degrees C. What is T2? Didn't tell me yet. Ammonia then flows into a heat exchanger. So now we're going to have a heat exchanger. And then it's going to flow out. What state should I call the outlet of the heat exchanger? 3. Good choice. All right. Then an exits is saturated vapor. So M dot 3 is also equal to M dot. Okay. What about P3? What about T3? Let's take a look at this a little bit. It exits at saturated vapor at 1.5 bar. 1.5 bar. Was there a pressure drop across the heat exchanger? It went in at 2 at 1.5 bar. It went out at 3 at 1.5 bar. That's good. That's our typical assumption. No pressure drop through a heat exchanger. But it comes out saturated vapor. All right? Okay. Determine the temperature of the ammonia after the throttling device. Then the part B, the temperature of the ammonia after the heat exchanger. Part B is easier to answer this case, isn't it? Can you tell me what the temperature at state 3 is? The pressure is 1.5 bar and it's saturated vapor. It's T-sat at that pressure, isn't it? It's the saturation temperature at the pressure 1.5 bar for ammonia. And when we look that up in our table, we find that it's negative 25.2 degrees C. Professor, look at it. It came way over here at 20 degrees C. It goes through the throttling device, then into a heat exchanger. You know what? I bet you there's a whole bunch of heat transfer out of that working fluid in that heat exchanger to make it come out at negative 25 degrees C. Well, let's do this. Let's back up and calculate the temperature at 2. How am I going to find the temperature at 2? Because this is wrong. It's not a great heat transfer out of the fluid to make it cold in that heat exchanger. There's actually a lot of heat pickup in that heat exchanger. You're adding heat and it's still going to come out at negative 25. That's the beauty of refrigeration. So let's continue. Let's analyze the throttling device by itself. We know that H1 is equal to H2, isn't it? Through the throttling device. I didn't leave a lot of room there, but H1 is equal to H2 for the throttling device, energy balance. We just did that. It's is it isothermal, isentropic, isenthalpic, isochoric, isobaric? I can't remember the name of that word. But anyway, it's constant entropy, not entropy, enthalpy. All right. So now, how do I get H1? Well, it's subcooled liquid. There's no subcooled liquid table. I used the approximation that it's H of F at 20 degrees C, and we get that it's equal to 274.26 kilojoules per kilogram. How about H2? What is the enthalpy at state 2? 274.26 kilojoules per kilogram because it's isenthalpic. Okay, well, what is the description of the state of the fluid at state 2? Well, I go to 1.5 bar and I get H of F and H of G, and I see that H of 2, guess what, is between them. This is 65.32 kilojoules per kilogram. This is 1410.61 kilojoules per kilogram. H of 2 is 274.26, right? It's between. What is the description of the fluid at state 2? It's two-phase liquid vapor. Can you calculate the quality at state 2? Sure, the quality at state 2 comes in at 0.155. That means by mass, 15% is vapor. What is the other 85%? Liquid. It's two-phase at that low pressure. Can you now tell me what the temperature is, T2? What is it? It's the saturation temperature. It's Tsat at 1.5 bar. So if it's Tsat at 1.5 bar, guess what T2 is? I'll put the answer up here. Negative 25.2 degrees C. What? This throws students for a loop. This is hard to understand. It goes through the throttling device. It's isenthalpic, and the lower pressure, some of it vaporizes right away to get into equilibrium, two-phase mixture, and the temperature drops. The temperature is cold. Then it goes into the heat exchanger, and the temperature stays at, because all it's doing inside the heat exchanger is boiling or evaporating the 85% that was remaining liquid. That heat exchanger we would call an evaporator. Evaporator. Why? Because what's the fluid doing inside of it? 85% of it is going from liquid to vapor, evaporating or vaporizing. The 15% vapor is already vapor. It'll just come out. The rest is saturated vapor. But the 85 needs to be vaporized at that constant pressure. All right, so now part C. What is the heat transfer to the ammonia in the heat exchanger in kilojoules per kilogram? You introduce a control volume for that heat exchanger, and you write an energy balance, and you have that the Q dot coming in equal to the mass flow rate of the refrigerant going through times the enthalpy exit minus the enthalpy inlet. Well, I need the enthalpy at state 2, 274.26. I need the enthalpy at 3. What's that? H of G at the 1.5 bar. That's the 1410.61 kilojoules per kilogram. True? So this lowercase q is q dot divided by m dot is equal to h3 minus h2. It's 1410.61 minus 274.26. Lowercase q is equal to 1,136 kilojoules per kilogram. That's the heat pickup in that evaporator from the surroundings going into the refrigerant to vaporize or evaporate to 85%, which was still in the liquid state. Last, I have just 3 minutes. Take a table like this and fill it out in your mind. Say to yourself, for the typical nozzle, what does maybe it look like a sketch? Does a nozzle look like that? Sure. What's a diffuser look like? Something opening up. What's a pump look like? Something like that. What's a compressor look like? Well, put a box there. What's a steam turbine look like? It expands, comes in, goes out. What's a hydraulic turbine look like? Yeah, put a box. How about a heat exchanger? Put a box. Throttling device? Put something like that. Okay, for each one of these, what about Q dot? Is a typical assumption that a control volume around that nozzle would have a lot of heat transfer? No. How about at work? No. What's the pressure doing? Going down. What's the temperature doing? Depends. Put uncertain. What's the velocity doing? And going up. Kinetic energy going up. Enthalpy going down. And just walk through this whole table. You got to do it. Watching somebody else do it's not going to be. But it's going to be a little challenging because we have different types of heat exchangers. Maybe I should have broken into 3 categories for heat exchangers. But maybe you think of the heat exchanger, which is the hot fluid and the cold fluid. And so you have 2 ins and 2 outs. Just do that heat exchanger. Okay? For that heat exchanger, is there Q dot with the surroundings? No. Work? No. Pressure drop from inlet to outlet on both? No, they're negligible. Temperature change? Yeah, typically you do. So what does the hot do? Typically goes down. What's the cold fluid do? Typically goes up. Typically. Because if you have one of them changing phase, then it could come in at the same temperature and go out at the same temperature, but it went and vaporized. Okay, that's the velocity. Typically, we neglect the change in velocity, and we neglect the change in the kinetic energy. And the hot fluid, the enthalpy change, it went down. And the cold fluid, the enthalpy change, goes up. Make sense? Okay, I'm out of time. Thank you for your attention, but please, as you're studying, make a sketch like this, fill it out, do it again, wad it up, throw it away, do it again, until these devices are clear in your mind what they're doing. Thank you.